We will now look at the plume filter. It's a new topic that I have added this year to this course, and we will start with a motivating example of the plume filter. And once we have looked at a motivating example, we will discuss in detail what a plume filter is. It's actually a highly efficient probabilistic data structure. But let's start with the problem. Imagine you want to build a spam filter. And I know there are many ways how you can build spam filters, but let's now assume we build a spam filter the following way. And it's not that important as actually a concrete spam filter, but this kind of problem can be applied to lots of other data processing problems. Imagine you have a stream of emails that are coming in, and what we have coming in are pairs, an email address from which the email was sent out, and the other part of the pair is the actual email itself. And our spam filter will work very simple. Imagine we have a whitelist of 1 billion allowed email addresses, the ones that we trust. And if an email comes from that 1 billion, from that set of 1 billion allowed email addresses, we are fine, at least in the initial stage. Maybe there could be some follow-up checks whether this is really spam with maybe some more advanced machine learning approach, but this is an early step we're doing. And we have this set S that has 1 billion allowed email addresses. And we will let them go through in the first phase because we believe that they are not spam. How do we determine which emails to let through? Because we have this list or this set of 1 billion allowed email addresses. The simplest way we can do is we could do a linear search. Each time we get an email, we look if the email address from the sender is in a set S, which contains these 1 billion allowed email addresses. And such a linear search in the set would be O of n. Do you think this is very efficient? If you think this is okay, maybe thumbs up. If you think this is maybe inefficient, thumbs down. Or green sticker means it's okay, red sticker means it's inefficient. I like to see your responses. And because I only get disagreements, means you have followed the course, and yes, that's not a very smart way. These email addresses can be sorted. And that's something that's quite helpful because we can sort email addresses just alphanumerically, for example. And then we can say we can use a binary search. And in a binary search in this sorted list then would be O of log n. And n is now, remember, 1 billion email addresses. So n equals 1 billion. So binary search leads to a massive speedup. We can have a balanced search tree, which is also O of log n if it balances well. We can also use a hash table where when the load factors fit and we keep resizing at the right time, we know the complexity is O of 1 expected. Obviously, O of n is the worst case because we may struggle with the hashing, whatever, but it's unlikely. That's why we say it's O of 1 expected. So these are speedups. However, we would always require that these data structures are stored fully in RAM. But our RAM on a modern computer is maybe 16 gigabytes, 32 gigabytes, whatever. And if I have a data set with billions of strings, at some point this may not be stored in my RAM anymore, and I need to do swapping on my hard disk or on my SSD. And when this requires disks lookups, it gets much, much slower because swapping RAM to the disk or even to an SSD is faster than a disk, but still it's super slow because the RAM is so much faster. And we could, even if we have a big RAM, we can say, well, it's maybe 10 billion entries that are allowed. So we can in the big data world, and later we will see lots of other use cases, not just the spam filtering, can easily run in a situation where such a set S does not fit into our RAM anymore. So it becomes super slow. There is a totally different approach we could do, which is a quantum search, assuming we have quantum computers large enough available and for entries that cannot be sorted. So if this here could not be sorted for some reason, we can actually use the quantum search or the Grover algorithm. And the Grover algorithm allows us to do a search in O of square root of n when we are unable to bring order into our entries. So with a quantum computer, this doesn't take O of n, but O of square root of n, but quantum computers are something we will see in the next lecture. But we can bring structure in it, so we would probably pick something like a hash table, a search tree, or something like this, or a binary search. But our RAM is not enough. Assume an email address is like 20 characters, so 20 bytes, but assuming we use ASCII, then it's quite reasonable that our S does not fit into the main memory anymore. So there are lots of things we can do. Is we can either use disk accesses, but disk accesses is super, super slow. And in your career, you will probably be working on large scale big data systems. So you will run throughout your career and also in your future courses in situations where your data just doesn't fit into your RAM and you need to devise new strategies for this. I teach the big data course in our department where we look exactly at such stuff. But disk lookups are not that great, so maybe we can think about a smarter method that requires, or a smarter method with which we can use the existing RAM to do an efficient lookup. And this is actually what the Bloom filter does. The Bloom filter, I mentioned before, is a probabilistic data structure. It's actually a very space efficient one, and it can do two very interesting things. When we have a data set in our Bloom filter, and we want to test whether an element is a member of that set stored in the Bloom filter, the Bloom filter will give two possible responses. So we store a data set in a Bloom filter, and we want to look up, is an element in the data set? We don't want to return it, we just want to do a check if it's part of the set. If it is definitely not in the data set, the Bloom filter will say no. So definitely not in the set. So it's a true negative, meaning if it's not in the set, the Bloom filter will tell us this. But the Bloom filter is probabilistic because false positives are possible. So it can say possibly in the set. And I want to look if an element is in the set, the Bloom filter may present me with a false positive and say it's possibly in the set, but the answer is wrong. But it gives us absolutely a negative answer if it's not in the set. So it's a probabilistic data structure. And we will now see how that probabilistic data structure works and why it's super helpful in a big data setting. And we will apply to our email problem. It's quite some maths today, and that's why we also have a double lecture today to explore this together. Now, assume we have 1 GB of RAM available. And a Bloom filter is very space efficient because we use in the RAM, we use the available RAM as a bit array. And if we have a gigabyte, that means we have 8 billion bits. Because 1 byte is 8 bits, So 1 gigabyte is 1 billion bytes, so 8 billion bits. And what we will do is that each position in that bit array will stand for something. We will soon visualize this and see this. We will also use hash functions. And we will start with a hash function h. Because we want to hash from the email address to a bucket. So we want to hash each member of S to a bit and set that bit either to 0 and 1. So each entry in the Bloom filter, so entry 0, 1, 2, 3, and so forth, they stand for one of those email addresses. And with a hash function, we can hash either to 0 or 1. And I'll try to visualize this in a moment, and we'll now devise step by step how that Bloom filter works, put it all together, we will visualize it, and then we will implement it in code. Because we've just started with the rough idea. So a Bloom filter consists of an array that has n bits. And these bits are initially all 0. And also one thing I want to say is part of this, what I'm presenting in this section here is from a very good book. It's called Mining of Massive Data Sets. I don't know if you know this book. If you know it, maybe thumbs up or thumbs down. It's a really good book about how to build algorithms that work on large scale data. It's not typically too relevant to this introductory course here in algorithms and data structures, but some of the explanations I'm using here are actually from this book. If you want to learn more about big data and how to process big data, take a look at the book. We discuss also the book in detail in my big data course, but this Bloom filter is actually a foundation data structure that we can discuss here already in the second semester, and that's why I've put it here. And we can contrast it quite well to the other concepts like the binary search, hash tables, and so forth. So we have an array with n bits, for example, the 8 billion bits as before. And initially, all bits are set to 0. Now we will not have just one hash function, but we will have multiple hash functions, k-many hash functions. And each hash function maps an entry or an element, like before an email address, or here we just call it a key. It maps this to n buckets, corresponding to the n bits of the bit array. We will soon see how we connect this. It's just the initial entries or initial elements of the Bloom filter. And we have our set S, which are the entries or the key values as we call them here, and we have m many. Don't mix up n and m. So we have n many bits in the Bloom filter and m many entries in our S. If you look into the literature, sometimes n and m gets mixed up, or not mixed up, but just used for the other way. Sometimes this is m and this is n, but here in my course, and if you look for I don't know, Wikipedia, they may use n and m just in the opposite way. So here the Bloom filter has n bits, and we have m many key values. And the purpose of the Bloom filter is we want to determine very, very quickly for all elements whose keys are in S, while we also reject most of the elements whose keys are not in S. And now we need to initialize the Bloom filter. So we initialize the bit array and set all of the entries to 0. Now, for each key value in S, that we take now each key value in S and we hash it using all of the k hash functions. We'll later see what these hash functions may look like and if we have any conditions on them. But each entry is now hashed with every hash function. And we will set to 1 each bit that is for which the hash function returns we set to 1 each bit for which the hash function h and some key value where we have this value here. So, but we'll see it in a moment. I think we'll visualize it and then we'll see it. We'll do the testing next. So imagine we have a set X, Y, and Z, which are the Plume filter represents the set X, Y, and Z. And these arrows here, they are colored and they show the positions in the bit array to each set element is mapped to. So we see we have an entry here, X, and it's mapped to some of the positions here. So X is mapped with the blue arrows to here, and to there. Y is mapped with the red arrows to here, and here. And for Z, we have these purple ones, which is mapped to other ones. So this was the initialization and adding the elements to the Plume filter. And we see a couple of parameters. We have 18 entries in here. So n is 18. And we have k many hash functions, which are 3 hash functions. Now, if I want to do the testing, and I want to test if a key v that arrives, I want to check, is it in the data set or not? What I will do is, I will apply each hash function to entry v, and I will check all of them that are 1 in the bit array. And if all of them are 1, so for an entry v, if every hash function returns 1, then I let the element through. However, if at least one of the hash functions maps the v to 0, then v cannot be in S. Because when I'm putting in an entry, and the entry X we saw was mapped to different positions to 1, but now I'm testing an entry W, and with the hash functions, I get multiple 1s, but also a 0. Then W cannot be in the Plume filter, because only entries that get hashed to all 1s can actually be part of the Plume filter the way I have defined it. I know this was lots of theory, and it's probably not that easy when you look at it for the first time, but we'll start implementing it soon. We will now apply this to our spam filtering, and then we start coding the Plume filter and see how it works. Now, if we apply this to our spam filter from before, so there are, say, 1 billion entries in S, which are the 1 billion email addresses we want to allow. About 1/8 of those bits will be 1. We assume this for now. That exact fraction of bits that is set to 1 will actually be slightly less than 1/8, but we'll discuss that later. Because the reason for this is that 2 members of S may hash to the same bit. So probably a little bit less than 1/8 of these entries will be 1. Now, when an element arrives, we hash its email address. And if the bit to which that email address hashes is 1, then we let the email through. But if the email address hashes to a 0, we definitely know that it's not in S. So we can drop that element. That would be spam. This here is just with a single hash function, because if we use a single hash function here for our setting with the email addresses, it could happen that some spam goes through. Actually, about 1/8 of the elements whose email address is not in S will happen to hash to a bit that is 1 and will be let through. But if we add more hash functions, like we have seen here in the visualization, then this error goes down massively. So more hash functions will reduce the error. We will later see how these variables are related to each other. So the size of the plume filter, the number of elements, as well as the number of hash functions. They all relate to each other. And we can, for example, reduce the error rate by adding more hash functions. We can make the plume filter larger. We'll later see how this works. We will now implement the plume filter, and then we run it, and then we will study it a little bit in greater detail. When I looked for implementations of the plume filter, I actually found a very helpful website, Geeks for Geeks, where there was an implementation of the plume filter that worked okay, but I've changed it a little bit. I've also changed some names, the variable names, so it fits the setting we have done so far. But that's why I'm just putting here the reference, because what I'll show you now in the coding session is inspired by the plume filter from that website. I need the math module. I need a package that is called MMH3. If you implement this on your own, probably if you use Anaconda or something, the MMH3 may not be part of your Python distribution, so you need to install that package. And we also need the bit array module, and in there is a class bit array, because we said we want to now put into our RAM a bit array, and we want to manipulate individual bits. So we don't put in a list or something, because that would be just a massive waste of space. Now, we are implementing the plume filter, and we will initialize it. What we need is a number of expected elements. And we also want to define the false positive probability, because we said false positives are possible, and we want to somehow initially, when we create an instance of the plume filter, determine or set what the false positive probability would be. Because if we want a very, very low false positive probability, this will impact some other quantities here in the plume filter. But we'll test this later for different false positive probabilities. And it also depends on the number of expected elements. If I have a lot of elements, I will probably put into my plume filter. This will also impact quantities in here. So, but we'll later see how they relate. We'll look at some of the maths later. So we are storing this now. So the number of expected elements will be stored as an attribute. The false positive probability will be stored. Then we need to know what is the size of my plume filter. So I need a new method that I call getSize. We will later see how we can implement getSize, because for this we need to study a little bit more maths. So the size would be the number of entries in our bit array. We also need to determine the hash count. So the hash count would be, and here the IDE or the IPython suggests me some incorrect suggestions. We will later see how we can implement get hash count, so the number of hash functions we would use, because the size of the plume filter bit array depends on the number of expected elements as well as the false positive probability, but we later see how they relate to each other. Assuming now we calculate the size and the hash count, we can then implement our bit array, and for this we are calling the class we have imported here on a certain size, and the size is calculated by getSize. And we will also say that in our bit array, initially we set all entries to 0, because this was also the description we followed, because later what we're doing next is we will set some of these entries to 1 based on the hashing, but initially all entries are 0. So now let's see how we can add an entry. So I have an item that I want to add. So I need to go through all my hash functions. Could be 5 hash functions, could be 100, we don't know. This we will later see how to calculate how many hash functions we will need. And eventually, I'm using this MMH3 package. How this works exactly is not relevant in this course. We've seen when we looked at hash tables how to generate hash codes, but the MMH3 simply generates hashes very, very well. So we can spread out the indexes as much as possible. So we have as little collisions as possible. And MMH3 is implemented for this. And what I want to hash is item plus I have another parameter I, which is just the index here. The I, in fact, is a seed in the hashing. And what I'm doing is I'm hashing the item with a seed, and the seed is the number of the hash functions, or for I in range. And this will return me some value, and I will take it modulo the size. So it actually gives me an index, and that index is a number in my bit array. And then I will look into my bit array at the index and set it to true. And this is exactly what we said before. We have an item, and we go through with each of the hash functions. The hash functions will return me an index. What I'm doing here, it's a valid index, and I'm setting that entry to 1. And there may be multiple hash functions. Now I've added an element, and now I'm doing the check if an item is in it. And what we've said before is we wanted to look for an item, and also that we are looking up, we will hash it, and we will wonder if all the corresponding indexes are true. And if one is not true, then that entry cannot be part of our Plume filter. So we're just doing the same as before. We're going through all the hash functions. We're taking the item and we are hashing it. And now I'm checking if the corresponding index is actually 1. Because it has to be 1 for that element to be in. So if that's not the case, so that I'm looking at a bit array at an index, and if that one is false, so if not something, if it's false, then this one here is true, then I'm returning false. Because I'm checking an element, and at least one of the hash functions has returned a false, or an index that is false. That means the element is not part of the Plume filter, because all elements that were added, I looked up the corresponding index from the hash function and set all the indexes to true. But now I found an index that is false. That means that element cannot be in, so I'm returning false, and it's a true negative. If I run through this list, the loop, and I have not returned false, then I'm returning true. But it may be true, the correct result. But as we've seen before, when we introduced the Plume filter, the true that I'm returning should be more interpreted like a possibly in the set, because false positive matches are possible with this data structure. So it's a probabilistic data structure. So we're almost done. All we need to do now is we need to implement get size and get hash count. So we need to know what's the optimal size and what's the optimal hash count. We don't know yet how to do this, so we can probably just do a quick mock-up and we will say, for example, the size is 100 and the hash count is 5. Or let's say 7. So we have 7 hash functions just in this mock-up because we don't know yet how to calculate this. And we can actually test it. So Plume filter. We expect like say 40 elements and we accept a false positive probability of say something like this of 5%. This doesn't make a difference at all yet in here because the size and the hash count are fixed. We will only later see how the size and the hash count depend on these two variables, but we can just test the Plume filter and we can add an item. For example, we can add a hello, a world, and a test. And now we can look up and do a check on hello. And yeah, my mistake. It's obviously Plume filter, which returns a true. For world, it returns a true. For test, it returns a true. And for not in, it returns a false. By chance, it may obviously return a false positive if I do more tests, but the not in is not in, so we definitely get a false. And but false positives are possible for the amount of entries we've added. This is extremely unlikely, but we will later see how this depends. One student asked if the size is n. Size is n, yes, and the number of expected elements is m. So m like Mars and n like nut. So size is n and m is the number of expected elements. And you can do more tests, like something like this, or an uppercase world, and we get a false. We can obviously look in and see what's the size of this or the hash count, but these are just the values we had set. So what we need to do is now we need to wonder about how does the size and the hash count actually depend on a number of elements and a false positive probability. For that, I will switch my slides. What I'm showing you here is just the code I have implemented. And when it comes to the false positives, let's study them now and understand them in greater detail, and then we can see how the size and the number of hash functions depends on the false positives. So we have a key value, or if a key value is an S, then the element will surely pass through the Plume filter. But if the key value is not in S, it might still pass because of the false positive. So we need to understand how to calculate the probability of a false positive. And calculating that false positive is a function of n, or as a function of n, the length or size of the bit array, and m, the number of elements of S, and k is the number of hash functions. So all of these variables, n, m, k, and the false positive probability, they all somehow are connected to each other. And for the explanation in detail, I will switch to my iPad. So we will now discuss how these variables interrelate. And for this, we need to study the false positives a little bit more in detail. What I'm saying now is written with lots of text in the slides if you want to do a revision. So I'll mainly just put the formulas here in these equations, but all the text that what I'm saying now, feel free to look in the slides. I will not write down all the text here on the board. So what we know is n is the number of bits in the array. So the size of the Bloom filter, number of bits in the array. And assume now we only have one hash function. So one hash function is for the beginning. And assume that a hash function selects each array position, so each position in this bit array, with equal probability. Then if n is the number of bits in the array, the probability that a certain bit is not set to 1 by a certain hash function during the insertion of an element is 1 minus 1 divided by n. Imagine you just set n to 1, then 1 minus 1 would be 0. So that the probability that a certain bit is not set to 1 by that hash function would be 0, which makes sense. And if you say n is now 2, then it's 1 minus a half, so it's a half. So this makes sense for one hash function. But this will become more complex now with multiple hash functions. And we will now have k hash functions. So if k is the number of hash functions, and there's a very important property for these hash functions, that these hash functions have no significant correlation between each other, then the probability that that one bit is not set to 1 by any of the hash functions is 1 minus 1 divided by n raised to the power of k, which also makes sense if you had an introduction to probability theory. So I'm repeating, if k is the number of hash functions, and then the probability that this bit is not set to 1 by any of the hash functions is 1 minus 1 minus n raised to the power of k. And then say your probability was a half, but you have lots of hash functions, then that probability gets super small. Now, there's a quick revision of your calculus, and I want to see if any of you remembers this. So I'm putting this here. Revision, well, put it here. It's from your calculus class, but it is very important to today's lecture as well. So you have a limit of 1 minus 1 divided by n raised to the power of n, where n goes towards infinity. Has any of you ever seen this limit? And do you remember the identity, what the result of this will be? Let's maybe start, send me a green reaction or a thumbs up if you have seen this kind of limit before. So 1 minus 1 divided by n raised to the power of n, where n goes towards infinite. So few people have seen it. Anyone still remembers what the result of this would be? So what's the limit? If you remember this as well, send me a green sticker or hands up. Now I only see red ones. In fact, it turns out that this is e to the power of -1, so 1 divided by e. This is something you've learned in your calculus class, or at least you have learned in your calculus class how to find this. If you forgot this, or by any chance you have not taken your calculus class yet, I will show you in the slides how you can find this identity. So how to actually get the limit of this and see that it's e to the power of -1. You just need some calculus. Not that difficult, actually. This is just a revision because we will need this now, because we need to do some trick here in this probability we have just explored. Remember, we are still looking at the false positives, and now we have introduced two variables, the number of bits in the array and the number of hash functions. And what we can do now is we can try to express this here, or try to approximate it. And we can say now for large n, so very important, for large n, so for large size, whatever large may mean, but not just for a few entries, then we can do something. So we put this down here, and we said 1 minus 1 divided by n raised to the power of k. We can rewrite this, and we can say it's 1 minus 1 divided by n. We can raise this to the power of n and raise this to the power of k divided by n, because eventually what would happen is these n's would just cancel each other out, because I raise this to the power of n and this to the power of k divided by n, then these n's would just be canceling each other out. So this is just an identity here. But because of my revision, I know that this here is e to the power of -1. What's very important is what I'm doing is an approximation, because I'm saying for large n, and in fact, we don't have infinitely large n. So this is approximately now e. The inner one is e to the power of -1. So this is e to the power of k divided by n. So somehow my k doesn't look very nice. So now. Now, why is this important? We will very soon see how we can relate all these variables we're interested in and later find the ideal size and the number of hash functions. Now, if we insert m many elements, so insert m elements, then the probability that a certain bit is still 0, as we've studied before the whole time, so this was 1 minus 1 divided by m raised to the power of k. That's the whole thing we've seen for the k hash functions. But we have m elements, and if we insert m many elements, then that probability that a certain bit is still 0 is this 1 minus 1 divided by n raised to the power of k raised to the power of m, or here then just k times m. And because we have just approximated this one here, remember this one in red, this one here, then this becomes approximately e to the power of k divided by n as before times m. So e to the power of minus k times m divided by n. And I just move the m into the fraction here. So it's k times m divided by n. Now, this was the probability that a certain bit is still 0. Now, the probability that a certain bit is 1, that bit is 1 would be just 1 minus the whole thing we have just calculated or derived. So 1 minus 1 minus 1 divided by n times or raised to the power of km. And then this would be just 1 minus e to the power of minus km divided by n. Now we're almost done with the derivation. It's just a little bit more maths, and then we're done. We've actually already done the most important part. And just as an intermediate revision, I'll just go through with you that we're all on the same page, because we wondered that the probability that a certain bit is 0 or not set to 1 by a certain hash function was the 1 minus 1 divided by n. We raise this to the power of k because we have k many hash functions. It is quick revision, and our term from here we have just re-expressed by taking advantage of this identity, and then we had the e to the power of minus k divided by n, and we just do this for m many elements. So we have introduced now more variables, n for the number of bits in the array, k for the number of hash functions, and m for the number of elements. And now we care about the probability that their certain bit is 1. So it's 1 minus the whole thing. So you see, step by step, we are making it there. But now we want to study the probability of false positives. So the probability of false positives, because we want to test the membership of an element that is not in the set. And each of the k array positions computed by the hash functions is 1 with a probability as before. So what has not changed is that each of the k array positions computed by the hash functions, because each hash function computes one of the positions, and I have k many hash functions, so it's about k many array positions and the probability for that is as before. Now, what we see is the probability of all of them being 1, which would cause the algorithm to return that false positive, because the false positive appears if all of the hash functions return me a 1 or return me positions that are 1. And then when I'm doing the test, I would get the false positive. So we would have an element that is not in. We would actually get it's in or most likely in. That's the false positive. And now we want to calculate what's the probability of that. And the false positive probability, we use, for example, a sigma or an epsilon, is, and I'm just using what I had up here, because this was that bit is 1. And now we have actually done this for k many array positions because we have k hash functions. So here I'm just taking the term from before, just the one we had used the whole time. So this was just this one here. But probability of false positives using k hash functions So I have to raise this whole term to the power of k, because I'm using each of the hash functions to do the test. And what I have calculated is here now is actually the probability of a false positive. So where I do the k many checks, and all of the checks return me a 1. And actually, this was for an element that is not part of the set. As we had this identity here before, I can just simplify this, and I can say my epsilon is approximately, because it's always approximations, 1 minus e to the power of minus km divided by n as before, and raise this to the power of k, because I'm doing k many checks. This is something you will notice in the literature. Is what I'm doing here is actually just an approximation. It's not strictly correct because we assume independence for the probabilities of each being in the set, or a probability of each bit being in the set. But assuming it is a close approximation, we are okay with this, but we assume that independence, and probably depending on the hash functions, that's not really the case, but it doesn't matter for now. It's just an approximation with which we keep working and that the literature here also uses. Now, what I want to know is the optimal number of hash functions. So optimal number of hash functions. The number of hash functions k must be a positive integer, a natural number. At least one hash function, maybe more, but it's always an integer and it's a positive, so it's a natural number. So for a given n and m, so I'm saying given n and m, so n was the size of the array and m is the number of elements. The value k that minimizes the false positive probability is, the literature says, n divided by m times the logarithm of 2. This one here minimizes the false positive probability. And this may be a float value, so you have to seal it, so you have to round it up to the next integer. The literature discusses in detail how to derive this, but given we know how to calculate E, it's actually fairly easy to figure this out in a few steps, but I'll show you soon how to do this. This is just an intermediate result we're taking now, that we say we know the optimal number of hash functions. And this was one thing we need to implement later. Remember, there were two functions missing, the number of hash functions. Now we know how to implement it. This is what the literature suggested. We'll later see how it can be derived. But we also need to know the optimal number of bits per element. So I'll first write this down, the optimal number of bits per element. For this, we will come back to very soon, or we'll come back very soon, how we calculated our epsilon. So what we need is the required number of bits n, the number of bits n, the size of the array, given m. So given is the number of elements. That's what was also one of the parameters for our constructor. So the number of expected elements, or here the number of inserted elements. And we have a desired false positive probability. So I'm just writing this here. So number of elements number of elements in the set, and the epsilon is the false positive probability. I noticed now at 3:45, a few students have joined because usually the lecture starts at 3:45, but you all were notified before that the lecture today started at 2 o'clock. So if you come in now in between, it may be a little difficult to catch up and you should be watching the recording. And if you remember from when we implemented the beginning of the Plume filter, these were exactly the things we passed to the Plume filter: the number of elements or expected elements in the set, as well as the false positive probability. So what we need now is our n. And one thing we assume to know here, and it comes from the literature, is the optimal number of k, so the optimal number of hash functions. And we can actually try to substitute this now into here, because we've defined how we can calculate our epsilon. And we have now a value for k, and we can try to plug this into the two spots. And I will do this now for you. So as before, the epsilon is 1 minus, and from up here you see e to the power of minus, this will be the k, and we see there is still the m and the n, so times m divided by n, and we raise this to the power of k. So what I'm putting here in blue is k, and k we had just defined, and we can just plug in that value for k. So this was n divided by m times ln2, and also here n divided by m times ln2. Very importantly, if you look at Wikipedia or other sources, I think they have just flipped n and m. So we use m for the number of elements in the set and n for the number of bits in the array, and the literature may just flip them. So if you look at Wikipedia, they will just these terms will just look the opposite, or these fractions would just be inverted. So make sure you always look in the literature before how n and m is defined. Now, if you simplify this, it's eventually just simple maths that you try to simplify this, because you will see that the n's and m's, and they all cancel each other out. What you will see is, and then you have this e to the power of ln2, and you have this minus up there. So this is your homework, trying to simplifying this, but it's just simple math, so we're not doing this here. You have seen this before. Eventually, this will be a half. So in green, this will eventually become a half if you simplify it. And so I'm putting this in green here, raised to the power of n divided by m times ln2. This can be further simplified. So I'm just putting here, just to remember you, it's the e that we looked at here. You can simplify this too, because we can say that the logarithm of epsilon, so we applied a logarithm on both sides of the equation. And if you apply the logarithm to the green part, you will get eventually minus n divided by m times ln2 squared. So this is the green part, just after applying the ln on both sides. So I'm writing here ln on both sides. Because you study in your maths course in detail how to do this, I'm just putting the result here. Feel free to test it at home and make sure you can do this derivation. And now I just need to move the variables around, and what I will find out is that n, the number of bits needed, will be minus m times ln2, sorry, my mistake, ln epsilon divided by ln2 squared. And this is the number of bits in my Bloom filter that I need, given my false positive rate and given the number of elements I want to insert. So we later need to implement this one because we wanted to know the size and we wanted to know the number of hash functions. So these are the two methods we still need to implement later. And then we are fairly done. But the headline of this chapter was not the optimal number of bits, but the optimal number of bits per element. And that's actually something quite interesting because with n, we have calculated a number of bits we need. But if I want to know how many bits per element, I need to divide all of this by m. And this will give me something like minus ln of epsilon divided by ln2 squared. And this is approximately minus 2.08 ln epsilon. If you have this here, you can also find out that in fact the corresponding number of hash functions can be derived or can be put in that relation as well, because what we know here is k is n divided by m times the logarithm of 2, and now we know the value of n divided by m. So in green, the n divided by m was just this one here. So we know then that k is minus ln of epsilon divided by ln2, because remember this was here the ln2, and I had an ln2 there, but divided by the ln2 squared, and eventually 1 ln of 2 stays. So what does all of this mean? This means that for a given false positive probability epsilon, the length of a Bloom filter n is proportional to the number of elements being filtered, which is m, and the required number of hash functions only depends on the target false positive probability. And this was all the maths for the Bloom filter. So now let's actually start implementing this. All we need to implement is the box in red and the other box. I will switch to my slides in a moment. Just for the ones that don't have access to the slides but want to see this well typed, we had started with the probability of false positives. Then we did this for k many hash functions. Here I show this identity that I required from you, which was the limit of n, the limit of 1 minus 1 divided by n raised to the power of n, where n goes towards infinity. This is in fact e to the power of minus 1. If you don't remember how to do this, here's the solution. We skipped that. And then we said we use that identity and plug it into the previous derivation, and we assume we do this for m many elements, and the probability that that bit is then 1 is 1 minus all of this, and we have derived the false positive probability. We assumed that the number of hash functions looks this way. This can also be derived in the literature, but here we just assumed it this way, and we looked at the optimal number of bits per element. And I thought it was probably easier to derive this on the whiteboard than just clicking through the slides. But I quickly wanted to show the slides, so they're also part of the video. And now we will implement just what we had done before. So, because before we implemented the Bloom filter, and we said we somehow need to calculate the size, we somehow need to calculate the hash count, and this is exactly what we're doing now. So I want to know the, so get hash count, self, obviously, and what we said was K is we take the size, which is n, divided by the number of expected elements m, and multiply it with the ln of 2. And in Python, we have the math module. You can say log of 2. Very importantly, I've also looked up the documentation of the math module in Python. The log is by default the logarithm to, or the natural logarithm, so to the base e. So the log 2 is not to base 10, but actually the natural logarithm. If you use a different math library, make sure that you use the right logarithm, because often log means base 10, but here in the math module, this is the natural logarithm, which is typically written ln, what we did before, but pay attention to this. We have calculated k, and we will seal it because k may be, or is most likely a float value, and we have to round it up to the next value and to the next natural number, and this is what seal does. The last one we need to implement is the get size. And get size, we also derived this, and we said that the n is minus this was m, the number of expected elements. We multiply this with the logarithm of the false positive probability. And here log again is the ln, the natural logarithm. And we divide this by taking the ln of 2 and square it. So raise it to the power of 2. And eventually we also need to seal this to the next natural, or to the, we round it up to the next larger natural number. So now we have implemented this very well, and based on the number of elements we will add to the Bloom filter and the false positive probability we are willing to accept, we calculate k and n and return them, and then they're used here for the size and the hash count. So let's test it. Bloom filter. So we said before we have 40 elements and we accept a 5% false positive probability. Just call this Bloom filter, not F Bloom filter. And we can just look into it and we see that the hash count is in fact 5 and the size is 250. I think before, when I just played with this, I said 7 hash functions and the size was 100. But what you will notice, obviously, if you reduce the probability, the false positive probability is now 1%, we will probably see that the hash functions goes up a little bit to 7 and the size grows to 384. If you say you accept a 10% false positive probability, let's test it, then it's 4 hash functions and the size is 192, but we may want to say 250 elements. Then we see still 4 hash functions, now 4 hash functions, and the size is 1199. But remember, these entries, they may be quite big. They could be long strings, whatever. And eventually, all we need is 1199 bits, which is very little. So this approach here can help us to store large amounts of data in the Plume filter and do a lookup where we either have most likely in the Plume filter or a definitely not. So we may have false positives, but we only have true negatives. So we have implemented the Plume filter, and it's obviously your task for at home to, you can experiment with the Plume filter, add some elements, try to create some false positives. You can most likely create some false positives by increasing this probability and just keep testing a lot of elements, and you will probably run into such a situation. And here is also the implementation. The implementation is also available in the resources.zip file. There is some coursework about the Plume filter, not much, because I've added the Plume filter this year for the first time, but you run the Plume filter discussed in class for different sizes of inputs M and different false positive probabilities and compare the required number of bits and hash functions and see if this makes sense to you. Now we've seen this Plume filter for emails, but it turns out that Plume filter has lots of interesting properties that we will study now. There's not much maths anymore because we've done the maths, but we just want to glue all of this together, and we'll look at a couple of use cases where the Plume filter is actually used. So we may run into false positives, but the Plume filter gives us a substantial space advantage, because otherwise, when we do such lookups, we just may run out of RAM, which will eventually lead to disk lookups, which are super expensive. So here we accept false positives and we can try to control them, but they are super space efficient compared to other data structures for the lookups. And the Plume filter does not store the data items at all, so we cannot just read them out, but we store these hashes or the indexes, what is a consequence of the hash function. And so that's something you need to bear in mind, but it's very helpful for doing very efficient lookups, and they are super space efficient. There are a couple of more things discussed in here. Feel free to read this if you wish. But one thing is probably the most important advantage. The Plume filter not only has a space advantage, but also a time advantage. The Plume filter has a very unusual property, and the unusual property is that the time needed to either add elements or to check whether an element is in the set is a fixed constant, O of k. So adding elements or checking whether an element is in the Plume filter does not depend on the number of elements added so far. It depends on it's O of k, so it depends on the number of hash functions. And that's super interesting because it's independent of the number of items already in the set. And that's something that is not the case, say, for a tree or a binary search or a hash table. But this is a very unusual property, which makes the Plume filter even more interesting. So feel free to think about what the consequences here could be. So you can also try to parallelize the Plume filter very well because you could do the K lookups independent and you can try to parallelize it and like this get even further speed ups. There are a few more considerations here in the slides that I will not read out all of them, but feel free to read them. But we've discussed most of this anyway. A Plume filter, you can see actually lots of applications for it. It was not just a spam filter, but in recent years, such key value stores have become very important. Like we've seen key value stores like the hash tables, but there are even now whole servers just doing key value lookups. And this is something that has become very popular in the big data world. And when you have a very large key value store, yes, it will not fit into the RAM anymore, and you need to do disk lookups. Like if you have a very large key value store as a sort of database, yes, then you need to do disk lookups when it's just a large database. But maybe in an early stage, you want to check, does the database, does the storage actually contain a specific key at all or not? And then the Plume filter, we could use a Plume filter as a first level before accessing the actual storage, but the Plume filter would be the first level we look at, and all the elements we've put into our big storage where lookups are expensive, we would first put these entries into the Plume filter, and the Plume filter could return a no and say, no, this element that you want to look up and the lookup is very expensive, we're reading it out, it's not in the storage because the Plume filter gives you a clear no. And then the Plume filter is very space and time efficient, so you can just store it in RAM, even for large amounts of data. Gives us a clear no, we're done. If it gives us a yes, the yes may be correct, but there could be a false positive. And but if the Plume filter says yes, then we're actually doing the disk lookup. In most of the cases, the disk lookup will return something, which is expensive, but we want to read it out. And in a few unfortunate cases, we have a false positive in the Plume filter, and the Plume filter will return yes, but the disk storage will return a no. But we can control these false positives as we've seen before. But it would be like a first level before you have a big database, reading from storage, reading from disk. We would put a Plume filter first and try to filter out the no's without doing expensive lookups. The Plume filter could also be used for cache filtering, for example. For example, there are content delivery networks. It's actually big business on the web that they deploy web caches around the world so we can read out from a cache very efficiently. But there are also these one-hit wonders, so things that only one specific person ever looked up and no one else. And do we really want to cache this? Well, probably not, because it will pollute our cache, because most of the lookups in such content delivery networks are actually one-hit wonders. Some studies say nearly 3/4 of the URLs accessed are one-hit wonders. And we could also use a Plume filter here in such a setting, because we don't want to waste disk space. So we could store the one-hit wonders in a webcam, or it would be a waste to store them in the space, since they will be or in the storage, because they will never be looked up again. And a Plume filter could be used to keep track of all URLs that are accessed by users. And when and an object is cached only when it has been accessed at least once before. So the object is only cached actually on its second request. And here we could use a Plume filter in order to significantly reduce the disk write workload, since most one-hit wonders are not written to the disk space. And in fact, Plume filters are used for these content delivery networks. And there's also a visualization here about this for cache filtering and the paper that studied this, where a Plume filter is used to prevent one-hit wonders from being stored in a web cache. and a plume filter has helped to massively decrease the rate of disk writes by nearly 1/2. So that leads to massive speed ups. And it turns out these plume filters are used in lots of other big data systems, like Google Bigtable uses plume filters, Apache HBase, Apache Cassandra, Postgres, and many others. They use plume filters to reduce the disk lookups for non-existent rows or columns. Bitcoin also used plume filters in the past to speed up wallet synchronization, but it turned out there were some privacy vulnerabilities with the implementation of plume filters, and this is something that was then dropped in that form. There also seems to be some natural link or net link to biology, like fruit flies seem to use a modified version of a plume filter to detect novelty of odors. I'm not a biologist, but the research reports that the way fruit flies detect novelty of odors seems to be some kind of plume filter that they use naturally.